we're here to discuss about the relationship between thermodynamic variables in adiabatic process. Well, before we proceed with our main equation that we are going to derive today, let me just tell you guys that in thermodynamics, we refer to the ratio of molar heat capacity at constant pressure by that at constant volume by a factor that is denoted by gamma. Now, it varies from monoatomic gases to diatomic gases and then to polyatomic gases, but we will discuss about that later. But today, we are just here to discuss about the relationship between the variables, which is P, V, and T in an adiabatic process. Alright, let us proceed with our main equation and its derivation. Alright, so by the first law of thermodynamics, we know that dq is equal to du plus dw, which means that if a system is supplied with a sufficient amount of energy, then that part of that energy will be used by the system to increase its internal energy, and another part will be used by the system to do external work. Alright, well, in an adiabatic process, we know that there is no exchange of energy by the surroundings and the system in the entire thing that we are dealing with. So we can say that in an adiabatic process, by default, dq is equal to 0. So we are left with the fact that in an adiabatic process, du plus dw is basically 0. And we proceed with the fact that to change the internal energy of a system, the equation stands that du is equal to cv times dt. And of course, in order for this to stand, we must consider that the number of moles of ideal gas we are dealing with is basically 1. So we can write du as cv dt. Alright, so we write that down. Plus the work done in the system is basically what? P dv. Alright, so let this be for some time. From the ideal gas equation, that is PV equals nRT. Well, I'm just going to write RT since we are dealing with 1 mole of ideal gas. We can differentiate this with respect to T, and we can derive that P ddt of V plus V ddt of P is basically what? R ddt of T. And further simplification takes us to the fact that alright, if we are done understanding this thing, then we can say that we can input this thing in this equation and we are left with alright, we are left with this thing. Now, in our previous lecture, we discussed that the difference between Cp and Cv is basically what? R. So this stands as, since R is basically the difference between Cp and Cv. And further simplification takes us to the fact that and the PCV dV and PCV dV cancel themselves off and we are left with, and this is just simple algebra. And now we are going to divide both sides by CV. And what are we left with now? The CVs divide themselves off over here, and VDP plus P CP over CV is 0 if we multiply this with dV, of course, yes. Now, at the start of our lecture, we said that in thermodynamics, we refer to the ratio of Cp over Cv as gamma. And if we input this over here, we get that VdP plus P times gamma times dV is basically 0. And now we divide the left hand side and right hand side by PV, and we are left with, alright, so can we not integrate this part? Of course we can. So the natural logarithm of P plus gamma, since this is a constant, times the natural logarithm of v is basically a constant. Let us denote that by k. Alright, so we are left with the natural logarithm of p plus the natural logarithm of v to the gamma is basically a constant. And then again, we are left with the natural logarithm of p times then v to the gamma is basically a constant. And this kind of applies for all general adiabatic processes. So we can say that for all adiabatic processes, PV to the gamma is basically constant. And similarly, if we use the relation that PV is equal to nRT, we can also substitute this P over here in terms of the other variables, and then again V over here in terms of the other variables, and we can also find out that TV to the power gamma minus 1 is basically a constant as well as the fact that T times P to the 1 minus gamma over gamma is a constant as well. That will be a homework for my students over here. So this is basically the relationship between the thermodynamic variables in an adiabatic process. Well, that's all.